This will be a complete review in everything covered in Dr. Maru's Chapter 16 on the reactions of aromatic compounds. The first reaction type we'll look at is electrophilic substitution. This reaction is favored because it keeps the aromaticity of the ring. Keep in mind that benzene doesn't do addition reactions like other unsaturated hydrocarbons because it breaks up the ring. An electrophile that replaces a hydrogen will react with benzene in a two-step mechanism. This mechanism will have intermediates that have three resonance structures. Let's look at the mechanism. First, the electrophile attacks. This makes a carbocation on the adjacent carbon that's resonance stabilized. This breaks up the aromaticity of the ring, so it's the rate determining step. To draw the resonance structures, we're going to move the positive charge around the ring 2 spaces at a time until we get back to where the electrophile was added. Now we just move the bonds around accordingly. Once you get here, this hydrogen gets taken away by a base, represented by B with the lone pair. This remakes the ring and gives us our final product. Remember that the charge will always be ortho or para to the carbon electrophile bond, so that it is delocalized over 3 atoms. Our next reaction type is halogenation. We're going to react a benzene with a chlorine or a bromine, along with a Lewis acid catalyst. Our products are going to be aryl halides. Because iodine is too low and fluorine is too fast, we can't use either of those. The reason why we need the Lewis acid is to act as a catalyst to make the halogen into a strong electrophile. This initial Br2 is a weak electrophile. When reacted with the Lewis acid, we get a partial positive charge on the bromine and a partial negative charge on the iron. Once this bond breaks, we get a very strong electrophile with a complete positive charge. Now let's look at the actual mechanism. It's very similar to the last one we just did. Up here we made our strong electrophile by using our Lewis acid. Just like last time, the electrophile adds onto the ring to make a carbocation. There are some resonance structures in this one too, so let's draw them the same way. Move the charge around by 2 atoms and fill in the double bonds. Once we get to the hydrogen, it gets taken away by a base. This gives us our final product. Notice that at the end, the catalyst is regenerated. Nitration and sulfonation is going to add on some functional groups to the ring. Nitration is really useful since the nitro group can be reduced to make the benzene and aniline. Let's look at some mechanisms. The mechanisms for both are basically the same. Let's just look at nitration. Just like in halogenation, the first step is generating the electrophile. We need a strong acid to do this. The acid will donate a hydrogen to this oxygen. To get rid of the positive charge on the oxygen, this bond goes over here to make a lone pair to give us water and our strong electrophile. Drawing the products of these kinds of reactions is very easy. Because the electrophile is so strong, it has no problem just tacking itself onto the ring. We can reduce this to make an aniline. Next type of reaction is Friedel-Crafts alkylation. We're going to treat benzene with an alkyl halide and a Lewis acid to get an alkyl benzene. Remember that vinyl and aryl halides can't undergo this type of reaction. Rearrangements can happen. Let's have a quick review of some of these compounds. Alkyl halides are compounds with one or more of its hydrogens replaced by a halogen atom like fluorine, chlorine, bromine, or iodine. This alkyl halide has 3 halogens attached. One is primary, one is secondary, and one is tertiary. Aryl halides are aromatic compounds that have one or more hydrogen atoms directly bonded to the ring replaced by a halogen. Vinyl halides have the general formula CH2 double bonded to CHX. Keep in mind that for both vinyl and aryl halides, the halogen is attached to an sp2 carbon. Acyl groups have the general formula RCO. It will have a double bond on an oxygen. It looks similar to a ketone because a ketone is an acyl group. An acylium ion are cations with the general formula RCO+. Let's look back at Friedel-Crafts alkylation. First, we need to make our electrophile. This is why we need the Lewis acid. We have a few options. If the chlorine is on a primary carbon, then there is only one step. This chlorine attacks the aluminum to give us our electrophile, which is the entire acid-base complex. There is an additional step if the chlorine is on a secondary or tertiary carbon. The first step is the same as last time, but this time, this bond will swing back onto the chlorine to make a very stable tertiary carbocation for the electrophile. Let's do the actual mechanism. Now that our electrophile is made, it adds onto the ring. The electrons in this CH bond swing down to get rid of the positive charge, leaving the hydrogen to be taken up by this chlorine over here. The molecule with the chlorine is the byproduct from when we made the electrophile. This gives us our HCl, reformed catalyst, and final product. Keep in mind that rearrangements can occur even if there was no free carbocation formed. We have to make sure that we keep the same number of carbons. Even though this one looks a little different, it still has 5 carbons. If a functional group can form a carbocation, it can be used as a starting material for this type of reaction. For example, protonation of an alkene or alcohol both make a carbocation, which can be used as the electrophile for this reaction. Keep in mind that alcohol also has to go through a dehydration reaction. In Friedel-Crafts acylation, we're going to treat a benzene ring with an acid chloride and AlCl3 to make a ketone. This reaction is called acylation because it adds on an acyl group to make a ketone. Let's go through the mechanism. This chlorine will attack this molecule to form the Lewis acid-base complex. This bond will swing down to the chlorine to make it happy. This gives us our resonance-stabilized acylium ion. This ion can react with benzene through electrophilic aromatic substitution. If a starting material has a benzene ring and an electrophile, all it needs is to be treated with AlCl3. Because it already contains an electrophile, we don't need to do much. When the acid is added, it makes a new carbon-carbon bond here to give us our product. Substituents will either increase or decrease the electron density in the ring. This affects electrophilic substitution. Let's take a look at the different effects substituents can have on rings. Inductive effects deal with whether the substituent donates or withdraws electron density. If the substituent is more electronegative than carbon, it will pull away and make the ring less rich. If there is a very polarizable group like CH3, the ring will be able to pull some of the electrons towards itself, making it become more electron-rich. Resonance effects only happens if the substituent has a lone pair or pi bonds. The effect is electron donating when resonance structures place a negative charge on the carbons of the ring, and withdrawing when it gives a positive charge. This one can take a little bit to draw, but it's not difficult. Let's look at all of the resonance structures of aniline. With our starting material, we move this lone pair down to make a double bond between the nitrogen and the ring. This disrupts the ring and puts a charge on the atom adjacent to the nitrogen bond. Just like before, let's move this charge around. Now let's fill in the bonds. Once this lone pair moves back here, it'll knock the electrons from this pi bond back onto the nitrogen to give us our starting material back. 3 of these structures place a negative charge on some of the atoms in the ring, so this effect is electron donating. If we have both inductive and resonance effects, we have to look at the entire molecule to determine which one is dominant. Some common electron donating groups are alkyl groups, or other groups with a nitrogen or oxygen with a lone pair bonded to a benzene ring. Some common withdrawing groups are halogens, or groups with an atom with a full or partial positive charge bonded to the ring. Now that we are familiar with the effects, we can move on to how they actually affect the reaction. Substituents can affect 2 things, rate and orientation. It can make the reaction go faster or slower, and it can influence the position of incoming substituents. All ortho pair directors, except for halogens, are activators. Because of the electron donating groups, these rings will react faster than benzene in all substituted reactions. All of these substituents are arc groups or have a non-bonded electron pair. Because we're reacting with an electron-poor electrophile, the more rich the ring is in electron density, the faster the reaction will be. Metadirectors are always deactivators. The electron withdrawing group makes the reaction slower since the electrophile isn't as drawn to it. These molecules will react slower than unsubstituted benzene in all reactions. All of these substituents will have a partial positive or fully positive charge on the bound atom. Metaproducts will predominate. Why do some substituents activate while others deactivate? To know, we have to look at the first step in the substitution mechanism. We add an electrophile to make a resonance stabilized carbocation. The more stable the cation, the faster the reaction. If we have something donating electrons, the cation will be more stable. If something is taking electrons, it'll be less stable. To determine which effect a substituent has, we have to look at the stability of all of the resonance structures. This can take a little while because of how many structures you have to draw. We're going to draw all of the structures for an ortho, meta, and para attack. In the ortho and para attack, this intermediate is more stable since all of the atoms have an octet. This makes the ortho and para products the preferred ones. Now let's take a look at this one. These all look fine until you remember that this nitrogen group has a positive charge on the nitrogen. In ortho and para, these two are adjacent to positive charges, making the preferred product the meta one. Let's get a summary of reactivity and directing effects. The groups above this solid line are activating groups. If these are added to the ring, it will react faster than unsubstituted benzene. Below this line are deactivating groups, which will make the ring react slower. The groups above this dotted line are ortho and para directors, so they'll make incoming substituents add in the ortho or para position. The groups below this dotted line are meta directors, so they'll make any incoming substituents add in the meta position. Keep in mind all ortho-para directors are arc groups or have a non-bonded electron pair, while all meta-directors have a full or partial positive charge. Let's take a look at a few common effects that come from activation and deactivation. If the ring has a strong donating group, the ring can undergo polyhalogenation when treated with these two molecules. Because of the complex that forms between it and the catalyst, rings with NH2 can't undergo Friedel-Crafts reactions. Rings with strong withdrawing groups also can't do these kinds of reactions. Because we add on an electron donor in Friedel-Crafts reactions, the ring is more reactive and can react to give us a polyalkylation product. This is not the same as polysubstitution, which can't happen for this type of reaction. If we have more than one substituent, we have to look at the effects from both. This group is an ortho-para director, while this group is a meta-director. For this one, we pick the position that both groups point to. In the one at the bottom, both are ortho-para directors. There is no overlap, so we can't use the method we used for the last one. Here we go with whichever one is stronger, which in this case is the top one. Keep in mind that there are still steric effect limitations. We can't substitute anything between two meta-substituents due to crowding. Nucleophilic aromatic substitution has two different mechanisms, addition-elimination and elimination-addition. We're going to use one of these two mechanisms to substitute a halogen on the benzene ring with a nucleophile. If there are more electron withdrawing groups, the reaction will be faster. The more electronegative the halogen is, the more reactive the molecule will be. Let's look at the mechanism for addition-elimination. This is similar to some of the reactions we looked at earlier. The nucleophile is going to come in and add right next to the halogen. This kicks off a lone pair and gives the adjacent atom a negative charge. The charge will move all around the ring 2 atoms at a time to kick off the halogen. When the nucleophile adds onto the ring in the first step, it makes a resonance stabilized carbon ion and breaks the aromaticity of the ring, making the first step the rate determining step. Keep in mind that this reaction only happens with aryl halides that have either ortho or para electron withdrawing substituents. Now, let's look at the elimination addition mechanism. First, this alcohol will take off the hydrogen. This leaves a negative charge on the atom adjacent to the halogen and gives us water. The lone pair will swing up to make a triple bond, which kicks off the halogen. This gives us our very reactive intermediate, benzene. A nucleophile will come over to this benzene and attach to where the halogen once was. It kicks off this lone pair and makes the adjacent atom negative again. The water that we got from step 1 will give back a hydrogen to give us our final product along with our reformed catalyst. Let's take a closer look at that benzene intermediate. This benzene intermediate is the reason why we get a mixture of products when we react with substituted aryl halides. In elimination addition, we can add either on the carbon directly bonded to the leaving group or the carbon adjacent to it. Benzylic CH bonds are weaker than usual. This is because homolysis gives us a resonance stabilized benzylic radical. This means that alkyl benzenes do selective bromination at this weak CH bond under radical conditions. It forms a benzylic halide. Let's look at the mechanism. Because this is a radical reaction, it undergoes initiation, propagation, and termination. When this bond is homolytically cleaved, we get two bromine radicals. This hydrogen is abstracted by one of the bromine radicals to give us a resonance stabilized benzylic radical. This radical then abstracts a bromine to make a benzyl bromine. This step forms another bromine radical, so this process can repeat until termination. You can get different reactions and products based on the conditions. If you treat the ring with Br2 and FeBr3, you have ionic conditions. This means that electrophilic aromatic substitution occurs. A hydrogen gets replaced by a bromine to yield ortho and para isomers. If you react with light or heat instead of FeBr3, you have radical conditions. In this case, the hydrogen will be substituted with the bromine on the benzylic carbon of the alkyl group. If you have an arene with at least one benzylic CH bond, you can treat it with KMnO4 to oxidize it to benzoic acid. If it has more than one alkyl group, you get dicarboxylic acids. Remember that you need to have a benzylic hydrogen in order to have oxidation. This molecule at the bottom doesn't have any hydrogens to give, so it can't be oxidized. Remember that Friedel-Crafts acylation forms ketones. These ketones can be reduced to alkyl benzenes in two different ways. We can use zinc and mercury with a strong acid to form a Clemmensen reduction. We can also use hydrazine and a strong base for a Wolff-Kishner reaction. If you want to make an alkyl benzene, you have two options: a one-step method with a Friedel-Crafts alkylation, or a two-step method using a Friedel-Crafts acylation to form a ketone followed by a reduction. While the second method does take longer, sometimes it has to be used to form some alkyl benzenes that can't be formed with the first one due to the rearrangement that happens. I might include it for the video for chapter 17, but I'm not sure what's happening with multi-step synthesis. Congratulations, you have made it to the end of chapter 16.